There we go. Okay, question 5. Calculate the gravitational field strength 2,000 kilometers from the surface of the Earth, given the radius 6.37 million meters. So for this we just use the field strength formula, big G times big M over R squared. Don't forget this comes simply from thinking about Fg, the gravitational force, as mg, and since we also know that an expression for that is now big G big M small m over R squared, it's pretty easy to put that in brackets. Straightforward, hopefully, for you to see that this part of that must be the same as small g. So if you ever forget this little expression here, it's fairly easy to derive again. Okay, so just plugging in the numbers in, 6.67 times 10 to the negative 11 for big G, 5.98 by 10 to the power of 24 for the mass, and just being careful to add on the 2 million meters. Okay, that's 2,000 kilometers, so that's 2 million meters. Adding that on to the 6.37 million meters, you'll get, 8.37 million meters squared on the bottom. In that case, with some careful number crunching, you should get the answer 5.69 newtons per kilogram. There. Number 6, assuming Earth to be a sphere, find its mean density from the following data. So for this we're going to use a couple of equations we've already become familiar with. We need to find the mass of the Earth first. We're going to use this equation. Solve it for mass. So mass equals R squared G, small g, over big G. And if you do this carefully using these figures here, that's the radius figure, this is for the small g, the field strength, and of course big G. You should end up with this figure down the bottom here, mass 5.98 again, times 10 to the power of 24. Now, to find the density, mean density of the Earth, we have to assume, of course, that the mass is evenly distributed, and use the expression for density, which hopefully you know, as the mass of the Earth divided by its volume. Now the volume, of course, for a sphere, perfect sphere, is 4/3 pi r cubed. So plugging in the radius of the Earth into there, cubing it, and then you can work out the volume. You should get this value here to 3 significant figures. It works out to be 5, 5, 2, 3, but the 3 is not significant since we've only got 3 figures for the radius, the gravitational field strength, and of course big G. Question 7, we are looking at the May-June paper from 2009, paper 4. A spherical planet has a diameter given at 1.2 times 10 to the power of 4, that should be, kilometers. The gravitational field strength at the surface of the planet is 8.6 newtons per kilogram. The planet may be assumed to be isolated in space and to have its mass concentrated at its center. Calculate the mass of the planet. So fairly straightforward, we're just going to use the same expression, solving for m this time. So the field strength equation, so m equals small g times the r squared over big G. And if you're careful with the substitution, you should get 4.64 times 10 to the 24, and chop off the 4 because we've only got 2 figures given everywhere, so we can only quote our final answer accurate to 2 significant figures. That should be to the power of 24. Okay, this is question 8. This is also from the May-June 2009 in 9 paper. The gravitational potential at a point x above the surface of a planet is negative 5.3 times 10 to the power of 7, that should read joules per kilogram. For a point y above the surface of the planet, the gravitational potential is negative 6.8 times 10 to the power of 7 joules per kilogram. State with a reason whether point x or point y is nearer to the planet. Well, by definition, you should know by now, hopefully, that gravitational potential is defined to be 0 at infinity. Therefore, the point which has a potential value closer to 0 must be closer to infinity from the planet, or in other words, higher above the planet. Therefore, since negative 5.3 is closer to 0 than negative 6.8, it must be point x. Point x must be nearer to the infinity. Oh, sorry, they're asking nearer to the planet. So in that case, it's point y for the same reason I just explained, but in reverse. So point y is closer because its value of potential is further from infinity, further from 0, and therefore it's further from infinity. Right. The same question continued. A rock falls radially, which just simply means along, or straight towards the centre of the planet, from rest towards the planet, from one point to the other. Calculate the final speed of the rock. So to do this, we're going to assume all the energy that was, in fact, gravitational potential energy goes into kinetic energy, and therefore the final speed of the rock. And if you like, all the work done by the force of gravity of the planet W is equal to the change of kinetic energy, or the gain of kinetic energy in this case, which resulted from a loss of gravitational potential energy given by the change of potential times the mass of the rock. So we can plug in the values. And in fact, before we do that, we're going to rearrange things a little bit. We're going to equate half mv squared with m delta phi. Notice the m's cancel. So we now get an expression for v 2 times the change of phi square rooted. And if you plug in a value for the change of phi, which is the difference between, what was it, 6.8 and 5.3? Yep, so it was 1.5 times 10 to the power of 7 joules per kilogram for the change of potential, times 2 you get 3 times 10 to the power of 7, all square rooted, will give you that answer there. But that's the two significant figures again, and that's times 10 to the power of 3. Okay, so now we're up to question 9. Find the gravitational potential at the surface of the Earth. Right, so all we're going to do is use the expression we've come to hopefully become familiar with. Phi is negative g big M over R. Plug in the numbers, negative 6.67 times 10 to the negative 11 times 5.98, the power of 24 for the mass of the Earth, and divide it by 6.4 million meters for the radius of the Earth, and you should get 6.23, the three significant figures, times 10 to the 7 joules per kilogram. And then B, at what distance from the centre of the Earth is the gravitational potential 1/2 of this value? Well, since you can see from this expression that phi is proportional to 1 over r, to get half the potential, we need to double the radius r. So it's simply, well, there it is there, twice 6.4 million, which is 12.8 million meters. And then last question here. What are we looking at? Oh, yes. The maximum potential that an object can gain as a result of moving a large distance from the Earth. Well, the largest possible distance we can move, of course, is to infinity. And since at infinity the potential is zero by definition, then the greatest amount of potential we can gain is in fact the amount required to get to zero, which would be 6.23 by 10 to the 7 joules per kilogram. Since at the surface of the Earth we have negative 6.23, we need to gain that much in order to get to a potential of zero at infinity. Question 10. The Moon's radius is 1600 kilometers and its surface gravity is 1.6 newtons per kilogram. Calculate the escape velocity from the lunar surface. In other words, what velocity would you need to reach in order to escape the Moon? Right, to do this, if you don't recall the equation for escape velocity in terms of small g, then you need to derive it again. So just to quickly run you through that. To reach infinity, we have to gain potential energy, EP, equal to gmm over r, because we initially have negative gmm over r when we're away from infinity. And what it means, of course, to get to infinity simply means you've escaped the influence of the Moon's gravitational force. So to do this, you have to gain that much kinetic energy, so we can equate that to kinetic energy. We get an expression for V in terms of these big constant values, cancelling out the m's again. We get V, the escape velocity, as 2 times big G big M over R, all square rooted. Now, that's not in terms of small g, but to get it in terms of small g, we simply recall that the equation is that one, gm over r squared. And so looking at this carefully, hopefully you can see that v squared is 2 times g times r, and therefore v is the square root of 2gr. That's the expression you want to use for this question. Now if you plug in these values, 1.6 for small g, 1.6 million meters for radius, times by 2, square root that, you should get this answer down the bottom here, 2.3 times 10 to the 3 meters per second. That's rounded from a 4-figure answer of 2262 meters per second, because of course we're only given 2 figures here and we're not sure about that one, but we have to assume 2 is the best we can do.